Hello and welcome to Software Architecture course. In this lecture, we are going to talk about another important quality parameter, which is testability. We will learn, just like the other quality attributes, what is testability and how exactly you want to capture testability requirements. How do you ensure through the architectural decisions testability can be achieved. So testability is something that's different from testing. Testing is a very well-known practice, an important part of the software development lifecycle that happens after the development, or it actually happens in parallel to the development. But testing and testability are two different things. We are going to learn testability as a requirement or as a quality attribute of the software, which as an architect you need to ensure. So testability means that the ease with which the software can be made to demonstrate its faults through the testing. This is an important thing that you must understand and be able to differentiate with the testing process itself. Testing is a process by which the testers test a software and tries to find out its faults. But testability means the software should be designed in such a way that it can demonstrate its faults through testing easily. So this is a bit different from doing testing. So our objective is that if a fault is present in a system, then we should be able to demonstrate, meaning that if the fault is present in a system, then we want it to fail during testing as quickly as possible, so that that fault is detected and fixed, and this fault is not present when the software is actually in operation. So that's the goal of testability, that we want the software to exhibit the fault through failure during testing. As you know, testing is an important activity and a huge amount of effort. In fact, at least 40% of the total development effort, if you basically count right from requirement to architecture to design, coding, etc. If you consider the entire development life cycle, 40% of that of the entire time goes, the entire effort that it actually goes for testing. So testing is a very important activity, and typically the testing is done by developers, testers, or even verification tools. So there are many specialized softwares for testing. For example, there are test harnesses, there are simple playback capability, there are specialized testing chambers available for some special purpose of testing. So let's look at, so when you're talking about testability, what we mean is essentially testable software, the software that can be easily tested. So in there is a very well-known statement made by a very well-known computer scientist called Dijkstra. So, and it's called the Dijkstra's thesis. And Dijkstra's thesis says that test cannot guarantee the absence of errors, but it can only show their presence. What that means is that if you do huge amount of testing, then, and through the testing, if you basically fix errors, the only thing that you can achieve by doing the testing is you can demonstrate that the errors exist in the software. But after completing the testing, this process of testing does not guarantee at all that all the errors are gone. So testing cannot guarantee the absence of error. It's not possible. What that implies is discovery of a new fault is basically remains as a probability, and we all know that you cannot make the software fault free. So fault discovery is a probability that the next test execution will fail and exhibit the fault. So we want the fault discovery to be absolutely deterministic, but unfortunately that is not the case. That can never happen. So therefore, uh, though we want a perfectly testable code, what that means is each component's internal state is controllable through inputs and outputs must be observable. That is a scenario that's impossible to achieve. But that's, if that can be achieved, then it becomes a perfectly testable code. So let me repeat this. Perfectly testable code is essentially a scenario or a property of a code where in that software code each component's internal state must be controllable, meaning that when you supply a different input, so this particular code you can imagine that as a blob, as a black box, and there are a set of inputs and there are a set of outputs. And what this property says is that by varying the inputs from external sources, by if you vary the inputs externally, then you must be able to control its internal state, meaning that you should be able to actually ensure that by changing the inputs you should be able to change the internal states. And output must be observable, meaning that if for every change in the state, if the system or the component generates any output of any form, that must be observable. So it actually expects almost every, in fact entire codes, all possible states and all possible outputs to be visible. Now only then it becomes testable. Now that's not possible at all, because the number of states are potentially infinite, and there could be, even if you kind of have a more smart way of defining states, having all possible states controllable through the inputs, it's actually practically not possible. So error-free software does not exist. Therefore we would always try to minimize the errors, but as an architect you must remember that getting such a perfectly testable code is impossible, because if it becomes perfectly testable, then it becomes error free, and both since error free code writing is not possible, perfectly testable code is also not possible. Then let's look at different testability scenarios that essentially you need to capture as the testability requirement. Then we will learn that how these testability requirements can be achieved through different architectural tactics. So who are the people who would be interested in testability? Essentially it could be the unit testers, typically the unit developers who are the unit testers by itself, or maybe integration tester, or maybe system tester, or maybe client acceptance team, maybe system user. They're all possible actors. So in this example it's a unit tester. What kind of stimulus these actors create? Basically the stimulus is, as soon as the milestone in the development process is met, things like completion of design, or it could be completion of coding, completion of integration, during that time this event, which is basically a testing event, is generated. So in this example the unit tester performs a unit test after the completion of coding. So what happens in the impacted part? So this stimulus, which is basically a requirement for testing, or someone wants to test it, so this can definitely impact on a component or the whole system. It can be impacted during design time, or development time, or compile time, or even integration time. Now if we look at the example here, in this example this unit test is done on a component, and this component has a controllable interface, and it is done when the component coding is complete. By controllable interface it means that it has got a set of inputs through which one can supply different variation of input parameters, and the system acts accordingly. Response action could be that test environment preparation. This is one action. Another action could be accessing of state values when the testing is going on. Another action could be access to the computed values. So in this example, the unit tester performs unit test, and then the tester observes the output for the inputs provided. What are the measurable response to first evaluate the quality of testability? One is the percentage of executable statements that are executed, which is also called code coverage. So code coverage typically should be high through the, so one of the requirement is that the code should be written in such a way that the code coverage should be high. Time to test, which should be minimal, the amount of time that one takes to test it. Time to prepare the test environment, that's also another response. In fact, it should be easy to essentially prepare the test environment. One shouldn't really spend a huge amount of time to prepare test environment. The length of the longest dependency chain in the test. So essentially there could be many dependency chain which might impact the overall testing activity itself. So this length should be reduced, and probability of failure if the fault exists, this should be very high. What that means is that if the fault exists in the code, then the probability that the system is that the application is going to fail should be very high, because if it does not fail in spite of the fault, then it's a very dangerous situation, because then you never know what the system is going to do or how the system is going to behave. If due to the fault, if the system does not fail but it continues to work unless you have the failure recovery mechanism in place, then it's a very dangerous situation. However, if you have a failure recovery mechanism in place in which it can capture the failure and then it can continue and can heal itself, then it's a different story. But what I'm talking about is not that scenario. I'm talking about a failure that I'm talking about a fault that exists, and but in spite of the fault being present, the system is not failing, but it is doing something. That's a very dangerous situation. So coverage of 85% is achieved in 2 hours. That could be the example of a measurable response. Let's look at the goal of testability tactics. Using the testability tactics, the architect should aim to reduce the high cost of testing when the software is modified. That's the goal. That the whole purpose of making the software testable is that every time there is a software is undergoing modification, it should be really easy for the tester to do the testing. Otherwise, if there is a high cost of setting up the environment, doing the testing, fixing the whole thing, then we say that it is not testable. And architect's goal should be to actually make it testable. There are 2 categories of testing. One is about introducing the controllability and observability to the system during the design itself, so that if it becomes more controllable and more observable, then it becomes better testable. The second one actually deals with reducing the complexity in the system's design. Let's look at various testability tactics. So we will look at the first one, which is managing the controllability and observability. Let's look at what are these. One is by introducing recording and playback mechanism. Another is introducing some specialized interface. Another is separating the interface and the implementation. This is also a tactics for modifiability. Executable assertions. That's also a technique that it's a part of good programming practice. Localize the data store. We'll talk about this when we explain this tactics in details. And sandboxing mechanism. Let's look at another approach of internal monitoring. In this technique, typically a built-in monitor is there in the system, which actually checks what's going on in the system when it is in operation. Managing of complexity is an important tactic. category, in which one can limit the structural complexity to improve the testability. Another could be limiting the non-determinism in the code itself. So let's look at control and observe the system states. So let's look at the first one, which is specialized interface for testing. So what is this specialized interface for testing? It is a type of interface which can control or capture various program variable values. Typically it is done for a component or a class. So either it is done either through a test harness or through normal execution. So this particular approach actually suggests that one use a special type of interface which is only used for a testing purpose. So it's a kind of a it's a very special purpose interface which a test harness can actually use, not a normal people, it's not exposed, or it's not to be used for normal operation. So through that interface, obviously this interface will have some implementation, and in the implementation one could write code to control and capture different variable values for a component. So through this special interface, one can also expose different types of metadata which could be useful for the test harness. Recording and playback mechanism is a technique. It's again a pretty well-known technique and old technique by which one can capture the information crossing an interface, and it can use it for input for further testing. It's like you run the system once and then record various activities, record the set of inputs given, record the set of also record the type of outputs that are observed, and this whole recording is stored, and then it can be played back later on multiple times. Localizing the state storage to, what does it mean is that essentially sometimes the system is quite complex and the whole testing procedure is not just you send an input and you get an output. It could be a series of activities. Now it may so happen that in that series of activities sometime in the middle the system crashes. Now in order to really go forward, okay, if every time the system crashes and you want to restart and then redo the testing, if for that you have to start from the beginning, then it's a waste of time, and that increases the testing time. So the goal should be to reduce that. So how one can do that? One technique is to basically create some kind of intermediate state which can be stored in a local state storage, so that this system or the subsystem under test can be started from that point onwards. In other words, you have to write the code in such a way that it is possible to start the component activity from somewhere from the middle. You don't really want to start the component activity from the beginning. So in other words, the mechanism to basically start the component from the middle and continue is a technique that one has to implement in the code itself. And for that, obviously, such a state needs to be stored, and it is expected that you store that state information in a local store or local storage. Now let's look at the next category of controlling and observing the system state. Controlling and observing the system state is about the interface and the implementation. Now if it is well designed, then interface and implementation are typically separated, and if so, then the implementation can be replaced by a stub for testing the rest of the system. So in other words, that if you have a system having a set of interfaces and you want to test only some part of it but not all, and you want to do it in the scenario where you know that some part of the interface is not well tested, you want to just skip it, then essentially for some of the interfaces the implementation can be a stub, so that it always goes through and you can come to the main point very quickly, which you want to test. So that's one of the technique by which you replace some uninteresting part with a stub, so that you can test the required part of the system. Sandboxing mechanism is about isolating the system from the real world to enable experimentation that is unconstrained by the worry about having to undo the consequences. So this is also a technique where you are testing a really complex application which is interacting with multiple other subsystems, and they might be live, and you want to test your system, and you want to in order to test that, you need to have a scenario where your system, which is under test, should be able to interact with the live system, get the real data. Only then this fault can be demonstrated. This is a very common example of a complex distributed application. So, but the thing is that if your system is faulty, and then if you plug in the faulty system into the real live network of other good systems, then because of the fault in this system, the other system might behave in a different way, and the whole operation might be impacted. And what we are talking about is basically a business critical operation. So in that case, what's essential is that the system that you are going to test, you need to put it in a sandbox in which a version of the other systems are actually kept in that sandbox, and your system is also there, and in that sandbox you can test it, you can crash the system as many times as you want to check what's going on, but that will not hamper the rest of the systems, because if because of the failure of one system, if the other system also fails, and then you have to undo those failures, it becomes really costly. Executable assertions is a technique in which assertion codes are usually inserted at desired locations in the code itself, so that these assertions are there to indicate when and where the program is in a faulty state. So this is more of a coding technique, but as an architect you need to come up with a design decision as to at what frequency you are going to insert these executable assertions. You have to create some guidelines for the developers. Managing complexity is another tactic in which let us look at different individual tactics here under this manage complexity category. Limiting structural complexity. So essentially what that means is that make the structure simple, make the architecture simple, avoid or resolve any cyclic dependencies between components that will create real problems during both compilation as well as testing. Isolate and encapsulate dependencies in an external environment, so that your testing time becomes easy, and then it's simple, takes less time. Reduce dependencies between the components in general, because if that's done, then what happens is that if a particular component undergoes modification and then undergoes testing, then the testing time the testing can be done only on that particular component which has undergone modification, and then possibly testing of other components are not necessary, or even if it is necessary, it need not be very exhaustive. But if the dependence is very high, then if a particular module is changed, then testing has to be done in all other components with which this one is very tightly coupled. That's the reason why it is said that you should reduce dependencies. Limiting non-determinism is essentially, if you are writing a multi-threaded program, then A multi-threaded program actually introduces non-determinism. You really do not know at different runs how different threads are going to behave, and if they are interacting with each other, and if the interaction is not done or not designed properly, in that case there could be a lot of non-determinism in terms of the state of these two threads which are running in parallel. Therefore, remove them as far as possible. Make it simple. Internal monitoring is essentially is a technique by which it's a built-in monitoring to test or to check the status of the system which is in operation. Typically, it is done through logging. One should be able to really turn it on or off. It is performed typically by instrumentation, for example, aspect-oriented programming, by which certain logging or certain kind of small code are inserted which can actually dump the system status as the system is running. Things like macros, instrumentation, etc. are very similar, and sometimes the instrumentation code can be put using AOP, and this can also help in doing the recording of the activities. In fact, this can actually make the system more observable. Let's look at different types of design checklists for testability. The first one is, as usual, allocation of responsibility, and let us see what are the different design checklists that as an architect you need to look at. Identify the services that are most critical and hence they need to be thoroughly tested. Identify the modules and subsystems which are offering these services. So first identify the services that are most critical, and then identify what are the modules and subsystems that are going to offer these services, and they need to be tested. For each such service, do the following. Ensure that the internal monitoring mechanism like logging is well designed so that one can turn it on, turn it off as and when it's required. Make sure that the allocation of functionality actually provides low coupling, which means reduces structural complexity, and strong separation of concern, and actually reduce the structural complexity. So these techniques are things that architects should keep in mind and basically create that as a design guideline. Design checklist is now we move on for testing data. So we have covered allocation of responsibilities. Now let's look at testing data for testability purpose. So let's identify the data entities that are related to the critical services. So we first identify the services and do the needful. Then after that we identify, for those critical services, let's identify the data entities that these services are using. So obviously those data entities need to be thoroughly tested. Now ensure that these data entities can be created or initialized, persisted, manipulated, and translated as follows. So one is that use a technique called state snapshot, where ensure that the values of these data entities can be captured if required while the system is in execution or at fault. What is meant by this is that for those critical services, identify the critical data entities that those services are going to use, and for those data entities now create some mechanism by which those data entity values can be captured if required during runtime, because if that can be captured, then when the system is at fault, then you can look at what were the values and then you can possibly fix it. Now this kind of technique earlier, when people used to use Linux based systems, and even today this is highly available in Windows and any other platforms. So those applications are compiled using different options, a debugger option, and then when the system is at fault, the system crashes and creates a huge core file, and that core file contains the values of these entities when the system crashed, and that helps during debugging as to what was the state. So what's being said here is that for certain special data entities, take special care and, if possible, create such kind of values, or create a mechanism by which a state snapshot can be created. Replay is another technique by which ensure that the desired values of these data entities can be set during the state, which is called a state injection, and one can do the testing and recreate the faulty behavior. What it means, what I mean by that is that, if you want to recreate the faulty behavior, have a mechanism by which the values of those data entities which cause the system to fail, have a mechanism to insert those values into the code, so that when the code starts running, it contains those values so that it can crash it again. In debugger, that's possible, but when we are talking about in general distributed systems which are actually running, so it's not that easy, because the debugger is not going to be there when the system is running. But the thing is that when you are testing the system, the system is being tested in a testing environment. So this replay capability should be there in the testing environments where one can inject those values directly. Let's look at the testing in infrastructure. So ask the question that, is it possible to inject faults into the communication channel and monitor the state of communication? This is one of the requirements, and it's also, and there are very special purpose tools available where in the communication channels different types of faults are injected, and then it is observed how the system behaves when such faults are there. Then also check and then decide whether it is possible to execute test suites and capture results for a distributed set of systems as opposed to one system. Is it really possible to really run such kind of test suites? Check that. This is important. Then testing for potential rest condition. Just check if it is possible to explicitly map process to processors or threads to processes. So that a rest condition happened when a process was allocated to a particular processor, and then there are multiple threads which are doing different things. So see if there is a possibility, if there are tools which can allow you to basically set those process to processor map and threads to process map manually, so that you can recreate the potential race condition. Let's look at some more, which is testing the resource binding. Ensure that the components that are bound later than the compile time, they can be tested in a late binding context. So example is that, suppose you are loading a driver on demand, and that's a feature of the system. If that's a feature of the system, then you should be able to test, and also during testing you should make sure that this scenario of loading a driver on demand is present, and you are going to test the rest of the systems assuming that the driver will be loaded on demand. And in the testing environment, you should definitely make sure that on demand loading is there. So suppose that because of the late binding there are some system failures, so you need to capture this particular scenario in the event of a failure, so that you can recreate a system state leading to the failure there. Ensure that the full range of binding possibilities can be tested. If there are multiple types of binding, even though all of them are late binding, if there are multiple ranges, as in terms of time when a component A is bound, when component B is bound, etc., if those timings are different, then you must test all these possible ranges. Resource management is also an important category here. Ensure that there are sufficient resources available to execute a test suite. As an architect, this is your responsibility. Ensure that the test environment is representative of the environment in which the system will run. This is also architect's responsibility, to basically ensure that the test environment is a representative of the environment that is going to be there during production. Ensure that the system provides means to test resource limits. So you should have some mechanism by which you should be able to test the different resource limits and observe how the system behaves. Capture the detailed resource usage for analysis. In the event of failure, you need to know when it failed, what was the CPU consumption, what was the memory consumption, did those consumption exceeded certain thresholds. Inject new resource limits into the system for the purpose of testing. And provide virtualized resources for testing is also a good way to do the testing, in which the virtualized resources actually have the predefined data, predefined set of services which are actually ideal for testing of software. Choice of tools is a very important part when you are doing the testing. As an architect, you must select a set of appropriate tools. So determine what tools are available to help achieve the testability scenario. So when you have basically captured the testability scenario or a set of testability scenarios, so then you must understand that do you have tools to really realize such testability scenario. Example is that, do you have a regression testing? Do you have fault injection mechanism? If one of the tactic is about recording and playback, do you have a tool which can support all this? Does your choice of tools support the type of testing you intend to carry on? You may want a fault injection, but in that case you need to have a tool that can support fault injection, injection of state values to recreate the fault. Such kind of things require a tool to be present, and the tool can capture the system state and can inject it. So you must understand if you have those tools available. If not, then you really cannot perform such kind of tests. Does a tool support capturing or injecting the data state? This is very important, where it can inject that data state and can recreate the failure directly.